stage. So Andrew Liu, I'm hoping I'm pronouncing that right, from Auburn University, will be talking about conflict triggers improvements in understanding speech in noise.
All right, thank you everyone. I'll be sharing with you about how conflict triggers improvements in understanding speech and noise. So throughout our daily lives, we encounter so much information that we need a set of mechanisms to help us filter the relevant information and respond appropriately. Cognitive control is a set of mental processes responsible for regulating attention and behavior. Whenever we encounter conflict, we deploy cognitive control to select appropriate perceptual information, inhibit inappropriate responses, and maintain relevant contextual information. So for example, in the UK, residents drive on the left lane. As an American, I'm used to driving on the right lane. So imagine that you are in the States and that you had to drive on the right lane. Imagine arriving at this empty traffic circle. Cognitive control is what is employed to stop yourself from going left in a clockwise direction and instead right in a counterclockwise direction. At your destination, whatever lane that may be, it also allows you to stop your natural response of heading towards the left lane and instead veering towards the right lane. In psychological research, the Stroop task is a common task used to gauge cognitive control abilities. In this task, conflict occurs when competing sources of information leads to incompatible mental representations. So for example, if you saw the word blue written in red ink, you would have to suppress the word blue and respond with the color presented, red. In these traditional tasks, participants improve as they progress through the task. One hypothesis is that the improved performance is due to conflict adaptation. Through conflict monitoring, participants improve due to the detection of conflict. For example, in the Stroop task, moving from trial 1 to trial 2, because of the font color mismatch, they can no longer use the dominant congruent response on trial 1 and become slower and less accurate on trial 2. However, on trial 3, they encounter a second incongruent trial. The typical finding here is that people are faster and more accurate. This is called conflict adaptation because they are improving after conflict. And the standard explanation for this is that when people encounter conflict, they recruit cognitive control. So the first time they encounter conflict, they have to engage in this effortful process and upregulate cognitive control. When they encounter conflict again, their cognitive control is activated and ready to go. This facilitates improvements in their responses. However, traditional tasks like these also present many confounds. For instance, feature binding is when the attributes of a stimulus are integrated together into a stimulus response record. So for example, the word blue and the mental representation of the color blue are two features integrated together. In this example, individuals have to break the binding from the previous stimulus response record in order to associate the stimulus with the new response, one that integrates the word blue with the mental representation of the color red. Processing these partial repetitions is time-consuming. It's more challenging than if participants were presented with a trial with completely different features, such as the third trial. Instead of purely conflict, partial repetitions could account for slower and less accurate responding. Contingency learning is another confound. Contingency learning is the association of a stimulus with a particular response through repeated presentations. So for example, the Stroop task has 4 response options. Usually, the task is designed to have an equal number of congruent and incongruent trials. However, due to the nature of the stimuli, This results in more varied incongruent trials than congruent trials. Thus, each individual encounters congruent stimulus much more frequently than incongruent ones. So in this case, participants will respond more quickly on congruent trials, not because the word and the font color match, but because they have seen the stimulus response pairing more often and have learned that the blue word is most likely yielding a blue color response. So similar to the traffic example at the beginning of this presentation, when we process language in our everyday lives, we do so in complex environments that require us to filter the relevant information and respond appropriately. So for example, we have to attend to a multitude of sounds, such as background conversations, television programs, traffic noise, and more. However, we're able to selectively engage in conversation amongst all the irrelevant sounds we encounter. Studies have shown that engaging cognitive control through training or conflict improves processing and comprehension of garden path sentences. Higher cognitive control ability is associated with better speech recognition for words with many lexical competitors. Increased brain activity in regions associated with cognitive control correlates with greater performance during speech recognition and noise tasks. So there's a relationship here between cognitive control, language processing, and speech recognition and noise. In this study, we're interested in how cognitive control relates to speech recognition and noise. Many studies have examined individual differences in cognitive control along with language processing or speech and noise. However, few examine causal relationships. So the goal of our study is to focus on how individuals use cognitive control to possibly improve language processing or speech recognition and noise. So listeners appear to activate phonological neighbors to differ from a target speech sound by a single phoneme during speech processing. So for instance, when hearing the word cat, there are more than 40 phonological neighbors that could be simultaneously activated. In many cases, listeners are also inundated with various sounds, such as other conversations happening around them. So in addition, neighborhood density has also been found to affect word recognition in noisy and quiet environments, suggesting that similar sounding words compete for selection across listening conditions. So cognitive control could possibly be used to better facilitate speech recognition and noise. We aim to discover, does cognitive control benefit speech recognition and noise? And does conflict adaptation occur in the absence of these task confounds? If we find improvements in the absence of such confounds, we can be confident that conflict adaptation is occurring. If it does, then the recruitment of cognitive control benefits speech recognition and noise. There were 32 native English speakers between 18 and 22 years of age. They had normal to corrected vision. They had normal hearing, as seen by their mean peer thrown thresholds, as seen here. Participants filled out a series of questionnaires and the Edinburgh Headiness Inventory. Then we conducted vision and audiological testing. Participants completed our novel speech recognition and noise task with pictures designed to introduce conflict. I'll go into that in a minute. And finally, they did a picture naming task. They were presented with all of the pictures used in our sprint task. Pictures were presented one at a time, and participants were instructed to give the first word that comes to mind. Now, traditional tasks have confounds that make it unclear how cognitive control influences speech recognition and noise. To address these questions, this study uses phonological competition to induce conflict. We developed a novel speech picture recognition and noise task to examine whether conflict monitoring takes place and does conflict detection induce subsequent improvements in performance. So the speech picture recognition and noise task, or SPRINT, uses 150 pictures selected from the bank of standardized stimuli. It's a free, standardized set of visual stimuli that have been normalized on more than 15 dimensions, such as name agreement, familiarity, complexity, among others. Pictures with 2 to 5 phonemes and name agreement above 50% were selected and paired with 150 spoken word recordings of a female native English speaker. In total, there were 60 congruent trials where the words matched the picture. In this example, the word recording bat matches the picture of the bat. There were 60 incongruent trials where the picture was paired with a phonological neighbor, thus inducing conflict. Here, the word recording scars is the phonological neighbor of the picture scarf. Lastly, there were 30 filler trials where the word was unrelated to the picture. Here is our sprint task, and here's how it's administered. For the duration of the task, a multi-talker babble played continuously at 60 decibels. The multi-talker babble sounds like many voices speaking at once. It sounds like a noisy cafeteria, but you can't make out any particular words. Each trial began with a fixation cross, followed by the presentation of a picture, which remained on screen for about 1,500 milliseconds. 500 milliseconds after picture onset, a spoken word was presented at +4 decibel signal to noise ratio, lasting roughly 800 milliseconds. The picture word pair was followed by a response period where participants were instructed to repeat the word that they heard, and then the next trial began. Congruent, incongruent, and filler stimuli were matched for picture name agreement, number of phonemes, neighborhood density, word frequency, and recordings were also selected for an average duration of 800 milliseconds. In our task, neither the word nor the picture are ever repeated. Each trial is a new event containing a never-before-seen stimulus-response pair, eliminating feature binding as a confound. Since each stimulus in our task appears only once, the stimulus-response pairs therefore appear in equal frequency in the congruent and incongruent conditions, which also eliminates contingency learning as a confound. Another advantage of using a speech recognition task is that each trial has thousands of possible responses, limited only by the number of words in the English language. This allows us to avoid ceiling effects that plague many traditional cognitive control tasks. Speech onset times and spectrograms were generated through an automated R script. All 150 spectrograms for each participant were visually inspected by 2 raters to correct for errors. If there were discrepancy between the 2 raters, it was resolved by a 3rd rater. We had 4 types of trials: IC, CC, CI, and II. There were 24 trials of each type, all were counterbalanced. So an incongruent trial is when a picture is presented with a recording of its phonological neighbor, thus inducing conflict. A congruent trial is when the picture matches the recording. And what we're interested in is how this preceding trial influences the current trial. So during these congruent trials, we expect relatively good performance. However, on CI trials, we expect the most errors and longest speech onset times because previously, participants hadn't encountered conflict. Now that they do, they need time to upregulate cognitive control. On II trials, however, after cognitive control is activated, we expect to see less errors and shorter speech onset times. In essence, conflict adaptation. Thus, we hypothesized that reduced accuracy and longer speech onset times on incongruent trials as compared to congruent trials, and 2, improved accuracy and shorter speech onset times on II trials compared to CI trials. So for this task, participants were instructed to generate the first word that comes to mind as they were presented with pictures used in our sprint task. On average, 94% of the pictures were correctly named in the first try. If participants required a second chance, on average, 98% of the pictures were correctly named at the second try. So from this task, the name agreement data shows that the vast majority of participants generated the picture names that we expected, suggesting a high likelihood of our phonological neighbors inducing conflict. Results show a main effect of current trial type. Participants perform significantly better on congruent trials than on incongruent trials. This showed that our stimuli do in fact induce conflict. If we take a moment to examine this graph, these 2 bars right here represent trial bars with preceding congruent trials. Preceding congruent trials, right? And the current trial for this bar is congruent. The current is incongruent. Same thing over here. Preceding trials were incongruent, and the current trial itself was congruent here and incongruent here. We found improvements following conflict. There was a 16% post-conflict accuracy boost on II trials as compared to CI trials. This could be evidence of conflict monitoring. However, could be arguments made that improvements were due to self-correcting whenever they incorrectly repeated a given word. In other tasks, studies have shown that participants can improve after making errors. So we only include trials that were preceded by correct trials too. If we direct your attention to the bar on the right, this means that on the preceding incongruent trial, so on the preceding incongruent trial, they had it correct here. And so we only included trials where they were correct on the previous trial. And again, we found a main effect of current trial type. Participants performed significantly better on congruent trials than incongruent trials. And we found a similar post-conflict accuracy boost. This time it was 14% on II trials as compared to CI trials. So they performed significantly better after encountering conflict. On speech onset times, we found exactly the same thing when we're looking at all trials. They performed better here, and they performed 30 milliseconds better here on II trials as compared to CI trials. When we do the same thing and we only look at trials where preceding trials were correct, we see essentially the same result. They did better in congruent trials. And here there was a 31% or 31 millisecond boost in speech onset time. So they're quicker by 31 milliseconds. Now, I know that 31 milliseconds might not seem like much, but you have to keep in mind that participants are also getting more accurate too. In many traditional tasks, participants tend to get slower as they get more accurate. Here, they're not only getting faster, they're also getting more accurate. So we showed that phonological conflict triggers improvements in accuracy and reaction times during speech recognition and noise. In essence, conflict adaptation. This provides evidence for conflict monitoring during speech and noise because they're improving their performance after conflict in the absence of feature binding and contingency learning confounds. This suggests that they're recruiting cognitive control to benefit speech recognition and noise. However, a limitation is that outside of the lab, people aren't presented with pictures as they're processing speech and noise. This is difficult to balance because when we study phenomena in a lab, we lack the realism. But outside of the lab, we risk introducing confounds. So one of our studies in development aims at addressing this issue. It involves alternating trials that have pictures and trials that have no pictures to examine a more natural processing of speech and noise. So would phonological competition improve speech recognition and noise without visual stimuli? For the future, a possible implication is that we could utilize the various cognitive control training techniques used in our field to possibly improve these related outcomes. And I'd like to thank my mentor, Dr. Susan Teubner-Rhodes, my fellow lab mates, and everyone else who made this research possible. And these are my references.
Thank you very much also for sticking to time so well. So we have plenty of time for questions.
You go.
I think we've got a question over there first.
Is this on? Yes. Thank you very much. It was really very interesting. I was curious about, so you're testing sequence effects, basically. Have you checked, or what are your thoughts on the fact that by on the wider sequence somehow, so if you're presenting a congruent pair, but it has been preceded by an incongruent pair, whether this has an effect? What are your thoughts on this? Thanks.
Well, That is a thought, but if we go down that train of thought, we could go like, multiple trials back. Commonly in the literature, we would examine the trial before it and to see how it influences the current trial. And in this case, although they encounter conflict before encountering, say, a congruent trial, we don't expect just the encountering an incongruent trial doesn't mean that they actively keep cognitive control active throughout the rest of the task, right? And so a congruent and congruent trial being, a couple spaces away from an incongruent trial, I just wouldn't expect that cognitive control is active, then, right? I would, maybe it could be, but I'm confident that it is active when the previous trial is incongruent, right? So although I can't say much about your sequence or the sequence you propose, at least with a sequence where the previous trial is incongruent, I can be more confident that it's active and we can better study it like that.
Thank you.
Okay.
I'm Joel Wallenberg, University of York. I might have just missed this, but did you also do the task with no noise? And would you expect the effects to be, the effect of preceding trial to be larger or smaller?
So we didn't do the task without noise. This specifically was a speech recognition and noise study. But if we don't include the noise and it's just the pictures and the words, I don't expect the task to be that difficult. I expect for them to really pick up the word and not really have that much conflict because they can hear the word clearly. We have conditions where the words are presented at +6 instead of +4 and +8 instead of +4, and preliminary data shows that they do get better as the decibel gets higher. And so if there were no background noise at all, they would just get everything right, I think.
So you just think as you decrease noise, the effects kind of level out?
Oh, as we increase the ratio, the noise or the sound level of the words presented, right? So there's a background noise of 60 decibels. It's not
Right, okay.
intelligible. You can't make it out. At +4, they have difficulty. At +6, it gets easier. At +8, it gets even easier. And so, yeah, without that noise, they would just get everything right.
I think there was another student question.
Hi, if you can. So my question relates to one of the works from your own lab, I guess, Eckert and Vaden in 2015-16, where the conclusion comes to the fact that there is an activation of adaptive control system, single opercular cortex, while listening to speech in noise. Here you say, so the question being, incongruent, and congruent. So how long would the effect of an incongruent trial followed by congruent trial, would it probably last in, let's say, if you were to be done in a neuroimaging study, what would your speculation be? So the activation of single opercular cortex?
That's a good question. That's a question where we'll have to really think about how to design the study to tackle how we can examine how long cognitive control remain active. With that study, it was really correlational. So we saw greater activities in regions associated with cognitive control. But just because there was a correlation there, it doesn't mean that we can make any causal inferences. And so we can add another layer to this study or expand this study. We're actually kind of doing that, actually. So we have a study where we have them go in the MRI machine and they do this exact task, right? And that's still in development. We have a pilot of like 2 participants, 3 participants. And so we're trying to tackle that too. But that's a good question. And I can't tell you as of yet how long I expect cognitive control to be active, when they encounter an incongruent trial. However, we hope to one day get there.
And the other question is about the experimental task. I believe I probably missed it. The background noise was 60 dB, I guess, right? And was it active like throughout the experiment or only for a trial?
Throughout.
And
So plays the whole time.
so my guess would be that probably participants also had there probably was an adaptation effect, for the background noise, because as you kept the background noise constant, and as the experiment progressed, wouldn't there be an adaptation effect? So because they suppress the background noise and then they only focus on the main experiment. I mean, it has been shown in previous studies as well, right? That if you continuously present the background noise.
That could be something that they might have done. We didn't check that because we're interested in the preceding incongruent trial, the introduction of conflict. But even if there is a suppression in that background noise and they get better, I don't expect for it to be that big of an influence, but we'll definitely look in on that. But I just don't expect it to be that big of an influence because performance is pretty stable across participants. And so I wouldn't expect a big influence of them suppressing that background noise. Now, as we move up in as we move up in decibels, I can see how that would, be easier when the words are presented at +6 or +8. That makes it easier. But yeah, thank you.
Yeah.
That was a good question.
Thanks.
Okay, there is one more question.
Wolya Kapatinsky, University of Oregon, really cool talk. So one thing I'm wondering is if there's kind of a Q reweighting account that is possible here that's not a kind of the main general inhibitor control thing, because your visual cues are actually fairly helpful, right? If you have a high noise level, if you just go with the picture, you'll be correct 50% of the time. But without the picture, you might be less correct, actually, if you're just guessing based on the auditory signal. So I'm wondering, if what could be going on here is that you downweigh the visual cues after an incongruent trial, rather than this being kind of a domain general cognitive control thing. So I guess like your experiment where you look at whether they also get better and the trials without pictures would get at it, but the current experiment, I think, could also have a Q reweighting explanation.
So to account for that problem, we had filler trials where the pictures weren't presented with a word that either were a neighbor or were its exact match, to keep them from thinking that the word would either be a neighbor or a match. In addition to that, the trials where it was a current congruent trial, they performed equally well regardless of what preceded it. And then when the previous trial was congruent and the current trial was incongruent, we saw exactly what we expected, right? And so there, as of yet, at least, there wasn't any indication that they were being primed from those trials where it was congruent to perform better in any way, right? But again, the trial that I mentioned will further go, solidify that and further account for that if that is a possible effect, which I don't think it is, because we did include the filler trials too, and we counterbalanced the conditions and everything.
I mean, I guess even with filler trials, imagine you have no auditory signal, right? You'd still get like 25% correct from going with the picture, and you'd be, at 1% correct if you just randomly guess the word.
Well, in this case, they are listening to the word, right?
Right.
And so it depends on what they pick up. And so they could produce a variety of sounds. It's not just correct or incorrect. So there are many more variations than, say, more of the traditional task I presented, where it's like hard, like, correct, incorrect. In this case, there's a huge variability in what they might have heard and what they might use or say with their vocabulary.
Thanks.
Okay, let's thank the speaker again.